it is the particle physics. First of all, Fernando, what is the particle physics? Whenever you're talking about particle physics, what is that?
Uh, the atoms.
It is just about the microscopic objects of this universe, right? Whenever we're talking about the physics, and in physics, whenever we're talking about the microscopic elements that build up the universe, right?
Yeah.
That build up the universe is known as the particle physics. You know that the characteristic constituent of this physics is basically a nucleus, right?
Yes, a nucleus which has protons and
Exactly, and that nucleus
neutrons.
is basically composed of two further things, the protons and the neutrons.
Yeah.
Initially, it was just regarded as that nucleus is basically made up of the neutrons and the protons. And apart from that, you also know that there are electrons residing around the nucleus as well. So there are electrons as well. But recent researches have shown that protons can also be subdivided into baryons and all other stuff, right?
Yeah.
Similarly, neutron is a baryon as well. And apart from the proton and nucleus inside the nucleus, we also do have some other compounds or the other elements inside the nucleus as well, such as the hadrons,
Yeah.
right? Apart from hadrons, we've got the nucleides, and apart from the nucleides, we've got some particle forces as well. The strong nuclear force that held all of this structure together. Okay, so in the particle physics, we are basically going to talk about all these constituents which make up a nucleus, right? So before talking about the particle physics, we need to have a very strong grip on the structure of atom, right? On the structure of atom, and this involves a bit of chemistry as well over here.
Yeah. I have taken chemistry for years, so
Okay, so for example, if you're talking about the structure of atom, who was the pioneer who who you know who guessed the presence of atom?
uh, I think it's one gold foil experiment. No, was that?
Exactly, and that was basically known as the Rutherford atomic model, right? It was basically the Rutherford's atomic model. And what did Rutherford told us? Rutherford just experimented, he took some gold foils, right? Placed it over here,
Yeah.
and he bombarded some alpha rays onto this gold foil. He bombarded some alpha rays onto this gold foil. And after the bombardment, whatever results he got, he postulated them. And what were those results? Do you know what was the postulates of this model, Fernando?
Uh, it showed how there's space in atoms.
Well, first of all, he showed that 99% of the alpha rays passed through the atom. They passed through the atom without any deflection, right? So about 99% of the alpha rays passed through the atom without any deflection. So what does this predicted about? This predicted that about 99% of the atom is an empty space. Okay. And what was second thing? That alpha rays into the center of atom. Alpha rays into the center of atom were diverted. And how they were diverted? They predicted the presence of a strong positive charge in the very center of an atom. And he predicted
Yeah.
that there would be a nucleus, right? So he predicted the presence of a nucleus in the very center of an atom. Apart from that, he also predicted that there are electrons which are present outside of nucleus and they keep on emitting energy. They keep on emitting energy while revolving. So the third postulate was the point of contention. It was true that electrons are present outside the nucleus. But when he said that the electrons are also keep on emitting energy while revolving around the nucleus, it was the bone of contention. That for example, people started arguing, right? For example, if this is a nucleus and this is an orbit around the nucleus, for example, in such a way like this one. For example, this is the orbit around the nucleus, and for example, we do have electrons over here, and these electrons keep on rotating around the nucleus by emitting enough amount of energy from them, right? So if they keep on emitting enough amount of energy about them, eventually there would be a time when electron would be having no energy, right? And if electron would be having no energy, or the energy of the electron would be zero, this electron would eventually fall inside the nucleus. This electron would eventually fall into the nucleus, right? And this can lead to the crumbling of this whole universe, which hasn't happened yet. Got it?
Yeah.
So this is the crumbling of the universe, and this cannot be happened. So due to this postulate, Rutherford's model was not that much of a successful thing. So basically, the recommendations were presented by the Bohr's atomic model, and it is very important to remember the postulates of the Bohr's atomic model. The postulates of the Bohr's atomic model. G. Fernando, what was the first postulate for the Bohr's atomic model?
Uh,
You just need to remember that the first postulate represented by the Bohr said that electrons revolve around a nucleus in certain circular paths which are known as orbits, right? They are known as orbits. They emit, he also said that they do emit or absorb energy. But when? They emit or absorb energy whenever they jump from one shell to another, right? What did the Rutherford said? Rutherford said that electron, for example, if present here and it keeps on rotating in the same orbit, it would still be emitting the energy. But what Bohr said, that electron would emit energy, but whenever it's going to jump from a higher energy level to a lower energy level. For example, if the electron is jumping from the third orbit into the first orbit, electron is supposed to be emitting energies, but not in all the cases. Got it, Fernando?
yeah.
Electron would be emitting energy, but only when it would be jumping from a higher energy level to a lower energy level. And similarly, electron would be absorbing energy whenever it would be going from a first shell into the third shell, right? Something like that. So this was appreciated, that electrons do not emit energy while keep on revolving in the same orbit. And the second postulate was that electrons are only allowed to revolve in those orbits in which the angular momentum, which is mvr, is equal to nh upon 2 pi. Electrons are only allowed to revolve in those orbits whose angular momentum, which is mvr, equals to nh upon 2 pi, where n is the number of orbit and where h is the g. What was the h, Fernando?
H is the what is H?
G.
What's H again?
H was a Planck's constant, right?
No, plan. Yeah, plan.
And the value of this constant was um, 6.634 into 10 raised to the power of negative 34 joules per second. Got it?
Yeah.
So, this is the Planck's constant, and you already know what the pi is. M is the mass of the electron, right? It is the mass of electron. What is the mass of electron, Fernando?
1 by 1840.
Yeah, it would make it is the mass of the electron in comparison to the proton, right? But if
Yeah.
you're talking about the actual mass of electron, it is 9.1 into 10 raised to the power of negative 31 kilograms, right?
Oh,
Apart from that, you also need to keep it in mind that v is the speed of the orbit, right? It is the
yeah.
speed of the orbit. And what does the speed, it is the speed of the orbit, but what does that mean? It is the speed of the electron in that orbit, right? Speed
Yeah.
of electron. And apart from that, whenever you're talking about the r is the radius of that orbit. It is the orbital radius. Does that make things fine? So you need to make sure of all these things. MVR equals to NH upon 2 pi. So this was the Bohr's atomic model. So in the 18th and the 19th century, many models were presented to discuss the atomic model, right? To discuss the structure of the atom. Rutherford and Rutherford and the Bohr was the successful ones, right? And if you're going to talk about another one of the important successful models is the plum pudding model. Plum pudding plum pudding model, and it was basically presented by the J.J. Thomson. G. Fernando, you might have heard about this model in chemistry. So what is that?
Is it the modern model?
And what is that about?
There's an central nucleus surrounded by electrons, right?
What else?
And is it the subshells come in?
Exactly. Um, Plum pudding model basically said that that electrons are basically diffused around the whole of the atom, right? They're not very fixed into a structure. You can just simply say that this model was about कि जो आपके पास whatever you're talking about, the negative charges which we nowadays call electrons, these negative charges or the electrons are spread evenly through a diffuse positive charge, right? They are spread
Yeah.
evenly. So what does that model look like? For example, if you're gonna have some positive charges all around like that. For example, if you ever see a pudding, you'll see the main ingredients to be spread out like that, right? They're just mixed like that. These are the positive charges, and through these positive charges, we've got the negative charges diffused out as well. This is how he viewed the atom as, right?
Yeah.
So this was the plum pudding model of the structure of the atom, and similarly many others. This was the structure of atom, and apart from that, uh, many other experiments were done to discover the electrons, protons, and the neutrons. Who discovered electron? J.J. Thomson, right?
Yeah.
And what was that experiment known as? It was a
The plum pudding,
no
right?
experiment. What was that? The name of that experiment? Cathode rays experiment. With the help of the cathode ray experiment, he invented the electrons, right? Similarly,
Oh,
whenever you talk about the neutrons were invented by the Chadwick, and protons were invented as a result of the CRO experiment as well. You know, I really can't recall the name of who invented the protons, but you know, it was invented as a result of the CRO experiment. Is that clear?
yeah.
Okay. Now we need to talk about the building. For example, the building nuclei. You need to know the basic things such as the atomic mass, atomic number, and all that stuff, right?
Yeah.
Okay. So first of all, what is the atomic mass? whenever you're talking
The
about it?
number of protons and neutrons
Exactly.
present.
It is the sum of the protons plus neutron and often represented as A, right?
Yeah.
And similarly, whenever you're going to talk about the number, atomic number is the
Number of protons and electrons.
exactly. It is just the number of protons, right? Not the electrons.
Yeah.
So it is just the number of proton
Of
and often
protons.
represented as Z. Now, if you want to calculate the number of neutron, remember that if you want to calculate
Proton
the
minus atomic number.
atomic mass minus the atomic number, right? Just subtract them
Yes.
up and you would be having the number of neutrons. For example, xaz. This is a symbolic representation of any element. And for example, I am taking it as the helium 42.
Yeah.
So how many neutrons would the helium be having?
2.
2, right? You just need to subtract the mass number with the atomic number and you would be having this thing. Is that clear?
Yes.
Okay. Now similarly, the next important thing that we need to talk about is an isotope. What is an isotope, Fernando?
They have the same number of protons but different number of neutrons.
Yep. So isotopes,
Same proton number and electron number but different neutron number.
exactly, they do have different number of neutrons, but that is not just as simple as you think of it. Uh, the basic definition of an isotope is that such atoms of the same element having same proton number but different neutron number. Did you get that?
Yeah.
But they do have different neutron number. This is what you call an isotope. Isotope are the atoms of the same element having same proton number but different neutron number. What does that mean basically? Remember that whenever you're talking about the proton number, and whenever you're talking about the neutron number, can you tell me what type of properties does the neutrons determine of an atom?
Uh, so proton number tells what element this is. Uh, Neutron number basically makes the element stable.
Mm-hmm.
The stability and radioactivity.
Well, apart from that, just keep this thing in mind as well. That whenever you're talking about the neutron number, remember that the number of neutrons basically determine the physical properties of an atom. They
Okay.
determine the physical properties of an atom. But whenever you're talking about the proton number, you know that the proton number should be equal to the electron number for an atom to be stable. And
Yeah.
electrons do interact with another atom due to the chemical bonding and all that stuff. So just keep this thing in mind that whenever you're talking about the protons basically tells you about the chemical properties of a substance, that where it's gonna react and where it would not be reacting. So it would be just telling you about the chemical properties. Is that clear?
Yeah.
So these are the isotopes. Now the next definition, an important one for the isotope, that these are the atoms, such atoms of same element having different physical properties, right? Having different physical properties but same chemical properties. Is that clear?
Yeah.
So they do have, whenever you're talking about them, whenever you're talking about the isotopes, they do have the same chemical properties, but they do have different physical properties. Like for example, if I'm going to talk about the carbon, the C12 6, C13 6, and C14 6. These are the three isotopes of carbon. And for example, if I'm talking about the oxygen, these are the two isotopes of oxygen, O16 8 and O17 8, right? But Fernando, keep that thing in mind that whenever you're talking about the carbon, C12, C13, and C14, all these three carbons do have the same chemical, because internally they are carbon, right? Internally
Yeah.
they are carbon, but their physical representation can be different. For example, C1216, C126 is is a very regular amount of carbon, and it basically you see in the coal, right? Whenever you talk about C136, it is a very rare isotope of carbon, and you see it in the buckyballs. And similarly, the most rarest of the isotope of the carbon is C14, and you see C14 6 in a case of a diamond. So you can see that all of these different substances are chemically the same carbon, but you would never see a coal exactly same in the shape of a diamond,
Diamond.
right? So you can see
Yeah.
that physically they are different, but internally they are carbon.
Yeah.
And same is the case with the oxygen, right? This oxygen is not radioactive, this oxygen is radioactive, but they do have different physical properties, but chemically they are the same things. Did you get that?
Yes.
So this is the most important thing to be kept in mind for any theoretical question, that whenever you're talking about the isotope, they can have different physical properties, but they would be having the same chemical properties. And why would they be having the same chemical properties? Because they do have the same number of protons. Is that clear?
Yeah.
Okay. The next thing that we need to talk about in particle physics are the nuclear equations. Now, what are the nuclear equations?
The nucleon equations. That's in like,
Well, whenever you're talking about the nuclear equations, they're basically the nuclear decay.
oh, alpha, gamma, beta.
Exactly. But first of all, I know that, whenever someone emits an alpha, beta, or gamma, it decays. But first of all, I need to know the reason behind the decay. That why does the decay eventually happen? Do you think O168 would be emitting any of these radioactive rays out of alpha, beta, and gamma?
No, it's stable.
But uh, you know, what about nitrogen 147? Would it be radioactive?
Nitrogen.
147, would it be a radioactive substance?
No.
Okay. Now, for example, let me talk about another stuff. For example, you've got a sulfur. Sulfur is 32 and 16. Do you think sulfur is radioactive, which we often use in explosions?
No.
No, sulfur is not radioactive as well. And similarly, for example, if I'm talking about a uranium 235 and 92, do you think this uranium is going to be radioactive?
Yes.
Now, how did you get that? What is the difference? Oxygen is an atom or uranium is an atom itself, but why uranium is radioactive and not the
The
oxygen?
high number of neutrons present in the element.
No, not the high. For example, let me write a higher number of neutron compound for you. For example, let me write, I guess ferrous 54 and 27. It do have 27 neutrons, but ferrous is nowhere near to be a radioactive substance. So the
No,
thing is not with that when someone do have higher number of neutron, it starts emitting rays. The thing is that whenever the internal structure of an atom would be unstable, and why would the internal structure of an atom be unstable? When the number of neutrons would not be equal to the number of protons, right? This is the initiation of the instability,
okay.
right? Whenever the number of
Yeah.
neutrons would not be equal to the number of protons, it would initiate the instability. Is that clear?
Yeah.
And you can see that uranium, not even uranium, thiamine, radium, radon, palladium, platinum, all these compounds which are radioactive, or cobalt, right? All these atoms, even C14 and 6, C14. You can see that there are only 6 neutrons, but still C14 is a radioactive substance. And the reason behind this, that it do have 6 sorry, it do have 6 neutrons, but it would not it do have 6 protons, but the number of neutrons would be 8 in this case.
Yeah,
Did you get that, Fernando?
yeah. So the neutron number, if there's more neutrons than protons, it's usually radioactive, right?
Exactly. No, the number of neutrons doesn't matter. The only thing matters is that the number of neutrons should not be equal to the number of protons. That brings out the instability, right? You can see
Oh,
that
yeah,
C146, it do have very small number of neutrons, right? It has
yeah,
only 6 protons and it has 8 neutrons, right? But it is still radioactive, and iron is still not radioactive, right? So it doesn't depend
yeah,
upon the number of neutrons. It depends upon that whether your element do have unequal number of protons or neutrons or not. If you do have, your element is going to be unstable. Did you get that? So for example, let's talk about, did you get the reason behind the radioactivity? That whenever the number of neutrons would not be equal to the number of protons, this would brought up instability in an atom. And that instability, this instability would brought up the radioactivity. Every atom is going to be radioactive due to this thing. Is that clear?
yeah.
Now, let's talk about the nuclear decay. First of all, you just need to remember that due to the 3 different types of radioactive radiation decay are also 3 types. The first decay, second decay, the third decay. The first one is the alpha decay whenever an atom emits alpha rays. The second one is the beta decay whenever an atom emits beta rays. The third type of decay is the gamma decay whenever an atom emits alpha rays, right? And you just need to keep this thing in mind, that whenever the nuclear decay is happening, you need to keep one thing in mind, that law of conservation of mass should be upheld. Law of conservation of mass should be confirmed. Law of conservation of energy should be upheld. Thirdly, law of conservation of charge should be upheld. And fourthly, law of conservation of momentum should be upheld. Did you get that? All these 4 conservation laws should be upheld whenever you're talking about the decays, right? Now thirdly, we need to talk about that what type of alpha, what is an alpha ray, what is a beta ray, what is a gamma ray. G Fernando, what is a alpha ray?
Uh, uh, that a decay that occurs at
No,
four.
I'm just asking you, what does the alpha ray is composed of? What are they made up
Oh,
of?
it's alpha particle,
It is a
helium,
Exactly,
alpha
it is a
particle.
helium. It consists of the nuclei of the helium, right? What about the beta ray? What are they composed of?
Uh, a electron.
Ex-
It's a neutron being split up into a proton and electron.
Can neutron be, your question is, can neutron be split into electron and proton?
Yeah, a neutron it gets split into proton and electron, right?
Exactly, it can. But this is not particle physics. Whenever we were talking about the subatomic physics, like the baryons and the production of hadrons, we'll be talking about that how does a neutron can produce an electron and proton. But over here we're talking about the beta rays, so remember that beta rays are the electrons, right? Beta rays are the electrons. And thirdly, whenever you have got these gamma rays, remember that these gamma rays are the neutrons, right? They do not carry any charge, they do not have any mass, they can just transfer energy from one object to another, right?
Yeah.
First of all, we are going to talk about the alpha ray, right? We are going to talk about the alpha ray or the alpha decay. So whenever you would be having a parent nuclei which is XAZ, and you would be producing a daughter nuclei Y plus a helium particle, remember that the atomic mass of the sister nuclei would decrease by 4. The atomic number would decrease by 2. Right? You can see that A minus 4 plus 4 should be equal to A again, and Z minus 2 plus 2 should be equal to Z again. Is that clear?
Yeah.
Now after that, secondly, whenever you're talking about such stuff, you've got the um, you do have the, for example, I'm just taking an example. For example, if you do have a uranium, uranium is 236 and 92, and due to the emission of the gamma rays, it produces thiamine, which is 232 and 90 plus helium. You can see that both the conservation of the masses, the conservation of the charges is being fulfilled. 236 is equal to 232 plus 4. 92 is equal to 90 plus 2. Is that clear?
Yeah. Yeah, this is clear.
Okay. Now for example, let's talk about another type of decay, and that is the beta decay. How does the beta decay happens? Whenever you're talking about the beta decay, what happens in a beta decay, for example, you've got a parent nuclei which is XAZ. It decomposes into a daughter nuclei which is Y plus the emission of an electron. You can see that the mass would remain the same because A plus 0 is going to be A again. But whenever you're talking about uh, the proton number, it would increase by 1 because Z plus 1, negative 1 would be equal to Z. Did you get that?
Yes.
So whenever, for example, the same uranium is undergoing a beta decay, it is supposed to be producing another isotope of uranium, which is 236 and 91, not an isotope, plus electron. You can see that, right? The laws of conservation of masses and the charges are upheld. So this is how the beta decay happens. Thirdly, we've got the gamma decay. And what does really happen in the gamma decay? For example, you've got a copper with a star. What does a star mean in chemistry? If you've got a star over a charge?
Uh, the cation.
Not the
We haven't learned the star notation, I think.
Well, the star notation basically shows that this copper is at the high energy state. It do have higher
Oh,
energy,
oh, okay.
and it has to get itself stable. So what that gonna do? It would be copper with the emission of the gamma rays or the neutrons, right? So this is what happens. During the gamma decay, charge would not change, mass would not change. The only thing that's gonna change is the energy. And you know that in a nuclear equation, we cannot represent the energy. So energy is supposed to be the same on both the sides. Did you get that?
Yeah.
So this is how the particle physics work. All this stuff, right? Apart from this thing, you should also have a particular good knowledge about the next topic which we're going to talk about is the fundamental particles.
Is there quartz?
Yep, we are going to talk about the fundamental particles. First of all, what are the fundamental particles? Fernando, should we start it because it is a bit confusing topic and we have already done some stuff, or is it fine for
Yeah,
you?
yeah, it's fine.
Okay, we can do that. Okay, first of all, what do you think about the particle physics? Sorry, the fundamental particles. What are the fundamental particles? First of all,
Uh, like
Before talking about the fundamental particle, you need to know the particle interaction theory. Fernando, it is a very basic question up till now that the age of the universe is about 13 billion years, right?
yeah,
This is the
yeah,
age of the
13.
universe, 13 billion years, the age of the earth as well, right? But the human beings were seen about 3 billion years ago, or any of these matters, the oldest of the human being was seen about 3 billion years. So there is a gap of 10 billion years, right? There's still a gap of
Yeah,
10 billion years. Now the question is, which many physicists have often raised, that what really happened in those 10 billion years, and what happened at the end of those 10 billion years, that we got matter. You know, the matter was introduced about 3 billion years ago. So what really happened that gave us the matter? All these
uh,
human beings, all these mountains, animals, grass, everything related to the earth, from where did it come from? And the only suitable answer for this production of the matter,
the Big Bang.
not the Big Bang happened 13 billion years ago. Big Bang doesn't lead to the production of the matter. And if Big Bang has happened, all the planets have been created. There is a sun as well. There is a galaxy. There are the galaxies as well. But what took 10 billion years to give us the first human being on the earth, and that is 3 billion years? How did the matter was produced? So scientists postulate that there might be a phenomenon known as a pair production might have happened. Pair production might have happened when two highly energetic beams might have collided among themselves, and it resulted into a production of electrons, right? And somewhere we would be having neutrons as well and protons as well initially, and all these neutrons, electrons and protons combined to produce the first atom of this universe, which led to the production of the matter. So there is no evidence for this thing to be happened. This is just a theory that neutron, proton, and electron. From where did the electrons come from? Due to the pair production. Pair production is a very important process in modern physics. So what is a pair
Okay.
production? That whenever two different photons collided among themselves, it leads to the production of an electron. Is that clear? So this is how electrons might have been created. But the question is, would there was just was there only these three particles which are neutron, proton, electrons, or would there be some other particles as well? And this is also unanswerable because we were not present at that time, right? So we
Yeah.
keep on digging inside the atom to discover those unknown atoms which would have been present in the earlier part of the universe, but they're not now. They're not present now. And those particles include hadrons, quarks, and all that stuff. Did you understand the basic concept from where it all comes
Yeah.
from? That there was no matter in the beginning of the universe, right? Big Bang happened 13 billion years ago. From where did that matter came from? So the basic answer for this thing is that there might have been pair production happen, but during that pair production, neutrons, protons, and electrons combine to produce an atom. But there could be a chance that there will be thousands of other subatomic particles as well, like quarks and all that stuff. So this is an atom. We have never stopped to dig inside the atom. We keep on digging inside the nucleus to discover many sort of new atoms. Is that clear?
Yeah.
So it has, by all that digging, we have produced a model, which is basically a particle zoo. Particle zoo. It is the standard model, also known as a standard model. And we need to talk about different types of fundamental particles in this category. Is that clear?
Yeah.
And first of all, the main standard model. In the main standard model, we have been provided with a atom with a fundamental particle that is known as a baryon. Gee, what is a baryon?
Uh, particle, the wave particle like thing inside the.
Remember that it is a particle present inside the nucleus, which is basically all those particles which are basically composed of three quarks. Remember that quark is a fundamental particle. Quark is a
Yeah,
fundamental particle, and it is such a fundamental, it is a fundamental particle, and whenever three quarks combine, it leads to the production of the baryon, right? And how many quarks do we have? We do have 6 quarks in total, and we want to name them. They would be up, there would be a
down,
down,
strange.
there would be a strange, there would be a bottom, and what were the other names? mm, I just What is the opposite of bottom?
Top,
Top.
top.
Top. There's a top, and then there is a opposite of the strange as
Opposite of
well,
strange.
right? Um, I just can't Can you Google it? 6 quarks. I just forgot the sixth name. Uh,
Charm.
yep, charm. The opposite of the strange is the charm quark. So these are the 6 quarks, and up and down are the most usable ones. So whenever you're talking about the baryon, they are made up of 3 quarks. For example, the important examples of the baryon are the proton and neutron. They are the protons and neutron. The composition of a proton is that whenever an up and down quark mixes up, it leads to the production of a proton. And whenever you're talking about a neutron, remember that whenever the up down quarks mix up, they produce a neutron. Is that clear? The
Yeah,
other examples of the baryons include the very important examples, the third one, it could be a sigma. Sigma is a baryon as well, present inside the atom. Similarly, there is an omega, and similarly, there is a lambda as well. All these quarks, right? We do not need to know the composition of these baryons, but you need to know the composition of a proton and a neutron, which is up down for the proton and up down for the neutron, right? And apart from that, some other information that you need to know about the baryon is that baryon do have a very short lifespan. They do have a very short lifespan in a free nature. And why is that short lifespan? Because they decay suddenly due to a strong nuclear force, right?
yeah,
They decay suddenly due to a strong nuclear force. Is that clear?
yeah.
The next type of the fundamental particles that we're gonna talk about are the mesons. What is a meson? Remember that whenever a quark gonna combine with an anti-quark, all of these 6 quarks do have, these 6 quarks do have some anti-quarks as well. Anti-quark means that it would be having the same mass, but there would be an opposite charge, right? The anti-quark of an up would be anti-up, which is represented by up hash. And what does the anti-quark mean? That it would be having the same mass but the opposite charge. Okay, the charge on the up is 2 by 3. So the charge on the anti-up is going to be negative 2 by 3. Similarly, charge on the down is 1 by 3. But the charge on the down and the anti-down is going to be negative 1 by 3, represented by d hash. Is that clear?
Yeah,
So remember that whenever you're talking about the quark or the anti-quark, whenever you're talking about the quark or the anti-quark, they mixes up to give you a meson. Is that clear? And
yeah,
the famous examples for the mesons are, they include pion. The composition of a pion is a up and an anti-down quark. Apart from that, another example for the meson is going to be the kaon. I'm really unsure about the composition, but it is a meson, right? And remember that their decay is very slow whenever they are traveling at a very relativistic speed. You understand what the relativistic speeds are?
no,
Relativistic speeds are whenever something travels with some speed that approaches to the speed of the light, right?
Oh, yeah. That's like value of C.
Exactly. So they undergo slow decay. They undergo slow decay when traveling at speed approaching to C, right? So this is the meson. After the meson, we've got the fourth category of the fundamental particles, and these are the hadrons. You know, we're really unsure about about the composition of the hadrons. The only information available for the hadron is that they're the particles that experience a strong force. Such particles which experience strong,
Isn't hadrons used for in like particle accelerators?
they are produced in the particle accelerators, right?
Okay.
You know, in particle accelerator is basically an instrument which produces all these fundamental particles, and we study them inside the particle accelerator. It is not something like hadron should always be produced in a particle accelerator, but whenever you accelerate a particle, uh, you make neutrons collide, hadron is created. And what is an hadron? Hadron is a particle which experiences strong nuclear force. Does that make things clear?
Yeah.
Okay. Secondly, uh, you should know that all the baryons or all the mesons, whenever you're talking about the baryons or the mesons, they are the fundamental particles, right? And all the baryons and mesons collectively are known as the hadrons. Is that clear? So this was a very complex sort of theory about the fundamental particles. If you would not be giving it a read from the book, you would not be able to understand the classification of the fundamental particles, right, Fernando?
Yeah.
So make sure after the lecture you give